Hello, this is Eric from UNC Charlotte. When programming shared memory systems, the basic blocks are threads and synchronization primitives like mutexes and condition variables. Writing a correct parallel program is hard, because one has to think about thread placement, avoiding race conditions, deadlocks, live locks, while still delivering on parallel performance. But when a programmer writes a parallel application, they do not want to think in such low-level constructs. They want to think in higher-level parallel patterns. They want to think in terms of loops, recursive decomposition, pipelines, parallel components. Today we will think through how to build a parallel loop construct with useful parallel semantics. This is the simplest example of for loops. It simply takes an array A and doubles every value into array B. One can achieve an equivalent parallel execution by creating a bunch of threads and distributing the iterations of the loop to the different threads, and by waiting for all the threads to be done. But when you write an application, you don't want to think in these terms. What the programmer wants to express is, I'm the programmer, and I guarantee that these iterations are independent. So go do them in parallel. All of the questions about how many threads, how do you synchronize those things, are unimportant implementation details. Reductions are somewhat a different case. Here, the iterations are not parallel. One could add a mutex to protect some and run the iterations in parallel, but the synchronization would kill all parallel performance. The correct way to parallelize this loop is to partition the iterations and have each partition work on a different local variable and reduce the local variables at the end. By mapping one thread to each partition, we would only need to take the mutex once per thread at the end, rather than once per iteration. Note that while the code is written with a particular partitioning here, the precise mapping of iterations to threads is not algorithmically important. What the programmer wants to express is that each thread will need a dedicated buffer. It is usually called thread local storage. And there is a need to run some code before the iterations of the loop in order to initialize the TLS. And there is a need to run some code afterward to perform the aggregation. Now that we have requirements, we can design one way this could work. Let's look at transform again. On the left, we show the serial code, and on the right, a version that presents the parallel semantic. There is an iteration space that goes from 0 to the size of the array, and we execute a task for each step between the two bounds. We also pass a function, here a lambda function, that will need to be executed for each task. The function takes the iteration that is being executed as a parameter. Having an object that implements this semantic is all we need to implement completely independent tasks. Reductions are a little bit more complicated. There is a need for thread-level storage. We could pass the type of the TLS as a template parameter, and instead of passing a single function to the object, we need to pass 3. The first one is the code that each thread needs to execute before doing any iterations, and that function would receive the TLS as a parameter. For reduce, it would simply initialize the TLS with 0. The second function is the function executed for each task. As before, it would take the identifier of the iteration, but also a reference to the TLS for that thread. Finally, the last function is executed by each thread at the end of the loop, and would typically be used to perform the reduction of TLS data into the global state. Is this the only way to design the abstraction we need? Certainly not, but it's a way that works. Some design decisions are baked in. For instance, there is no lock taken by the after-iterations function when accessing sum. So the assumption is that after-iteration functions are executed exclusively. Only one thread can execute that function at once. If the abstraction has not been thought through carefully, then reductions would not be possible, and the abstraction would be too narrow to be useful. But at the other extreme, a very generic abstraction, such as threads and locks, does not help provide a high-level semantic. When designing a high-level semantic, you want the abstraction to be as generic as possible while remaining easy to program. Often, the parallel features would be encapsulated in an object to allow to configure how the execution would happen. So you would have functions to set how many threads would be used, how the threads are placed, and which iterations each thread takes, or to provide features like thread pooling and profiling. This separates the concern when implementing an application. You can think about expressing the parallelism in loops without having to care about the details of how they would get executed. Potentially, you could have different programmers working on the algorithmics of the application and its deployment. This principle was taken to the extreme by the Halide programming language. It enables expressing complex imaging applications and separate algorithms from execution. In this video, we saw that higher-level semantic can be useful in enabling non-parallel computing experts to program in parallel, as long as their applications fall into a well-defined semantic. By studying use cases, we can extract a higher-level semantic for some applications. Here, we saw how to design a parallel loop semantic, but some other parallel semantic can be useful.